If you watched part one, you already know the big idea. Reinforcement learning is about learning from consequences over time. Today we're going to lock in the vocabulary because once the terms make sense, agent, state, actions, reward, everything else in RL starts feeling way less mysterious. And I promise, after this video, when you see phrases like trajectory, return, discount factor gamma, or policy optimization, you won't feel like you're reading a different language. You'll be like, oh, that's just the agent's experience, the score it tries to maximize, and the rule it uses to choose actions. Let's build this mental model cleanly. In reinforcement learning, we always imagine a loop. Something is making decisions, something reacts. Then the decision maker gets feedback and tries again. That's it. The decision maker is called the agent. The thing it's interacting with is the environment. And the environment is basically everything outside the agent. The game, the robot's physics, the market simulator, the recommendation platform, whatever generates consequences. So whenever you hear RL people talk, they're basically describing variations of this loop. Agent observes, agent acts, environment responds, agent receives reward, repeat. Now let's name each piece. The agent is the learner. It could be a neural network, a table of values, a set of rules, anything that can choose actions. The environment is the world that responds. It takes the agent's action and returns two things: the next situation the agent is in and a reward signal. A nice way to think of it is, the environment is like a game engine. The agent presses buttons. The engine updates the world. The engine gives you points and a new screen. And notice something important. In supervised learning, you normally get the correct label. In RL, the environment does not give you the correct action. It just gives you consequences. So the agent's job is not guess the right answer. The agent's job is figure out what actions lead to higher total reward over time. That over time part is where all the interesting complexity comes from. Next vocabulary, state and observation. In the cleanest textbook version of RL, the environment has a state. The state is a complete description of the world at that moment. In chess, it's the full board position. In a robot simulation, it's positions, velocities, joint angles, everything. If the agent sees the full state, then decision-making is fully informed. That's the classic setting. But in real life, the agent often doesn't get the full truth of the world. It gets an observation, a partial view. A self-driving car doesn't see the true state. It gets sensor readings. A poker agent doesn't see the opponent's cards. A recommendation system doesn't know your entire mental state. It just sees clicks and watch time. So, state equals the full internal situation of the environment. Observation equals what the agent actually gets to see. If the observation fully matches the state, life is simpler. If the observation is incomplete, the agent needs memory or some way to infer what's going on. That's where recurrent networks or belief states come into play. But that's later in the series. For now, whenever you see RL papers switch from state to observation, they're usually saying, the agent doesn't see everything. Now, actions. An action is exactly what it sounds like, the choice the agent makes at each step. In Atari games, actions are button presses: left, right, jump, shoot. In robotics, actions might be joint torques or target angles. In recommendations, an action could be Show this item next. In LLM-ish RL setups, the action might literally be choose the next token, though usually we bundle that into a sequence. Actions come in two common types. Discrete actions, choose from a small set, like move left or move right. Continuous actions, choose a real valued control signal, like motor torque. Discrete actions tend to be easier to start with. Continuous actions are more realistic for physical control, but they introduce extra learning challenges. Now for the most misunderstood piece, reward. Reward is not the same thing as success. Reward is a number the environment gives after an action that nudges learning in a direction. In a game, reward might be points. In robotics, reward might be +1 if you lifted the cube, small penalty if you drop it. In recommendations, reward might be watch time or clicks. In RLHF style setups for LLMS, reward can come from preferences. Humans pick which answer is better, and that gets turned into a reward score. Here's the trap. If your reward is badly designed, the agent will absolutely exploit it. You might want finish the level, but your reward accidentally encourages stand still to avoid losing points, and your agent becomes the world's best statue. That's reward hacking, and it's not a rare edge case. It's basically the default outcome if the reward doesn't match what you truly want. So reward is not a magical truth signal. It's a training signal, and designing it well is an art. Now we add time structure. A lot of RL problems are broken into episodes. An episode is one run from start to finish. In a game, start level, play, game over. That's an episode. In a robot task, reset the scene, attempt pick and place, success, failure, reset. That's an episode. Each episode is made of steps. At each step, observation, arrow action, arrow, reward arrow, next observation. Some environments don't have clear endings. Those are continuing tasks. Think of a recommendation feed. It can go forever. In those cases, we often still create artificial episodes for training convenience, like fixed-length chunks. But the mental model stays the same. Now we name the agent's lived experience. A trajectory, also called a rollout, is the sequence of what happened. Observations, actions, rewards, and sometimes states. Imagine you record a gameplay session. Every screen, every button press, every point earned. That recording is a trajectory. Why do we care? Because RL learning algorithms often train from batches of trajectories. They look at what the agent tried, what rewards followed, and update the policy to make good behaviors more likely. So when someone says collect rollouts, they mean run the agent, record what happens. Okay, here's a key concept, return. Reward is immediate, like you got +1 now. Return is the total score over time. If your agent gets rewards across a whole episode, the return is basically reward now plus reward later plus reward even later. That sounds simple, but it introduces an important problem. Sometimes you do something that looks bad now, but sets you up to win later. That's why RL is hard. The agent has to connect early actions to delayed consequences. You'll often see return written as G, 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 or RRR with a time index, but you don't need the math yet. Just understand the idea. Return is the total reward outcome the agent is trying to maximize. Now we introduce one of RL's most famous symbols, gamma, written as gamma. Gamma is the discount factor. It controls how much the agent values future rewards compared to immediate rewards. If gamma is small, the agent is impatient. It mostly cares about rewards right now. If gamma is close to 1, the agent is far-sighted. It's willing to sacrifice now to win later. Why discount at all? Partly for mathematical stability, partly because in many environments the future is uncertain, and discounting helps focus learning. In practical terms, a low gamma tends to create short-term strategies. A high gamma tends to create long-term planning, and you can actually feel this in behavior. In a game, low gamma agents might chase small points right away. High gamma agents might learn to position themselves for bigger rewards later. So gamma is basically the knob that says, how much do we care about the distant future? Now for the most central term, policy. A policy is the agent's strategy. It's the rule that maps what the agent observes to what action it takes. If you want the simplest definition, policy equals how the agent chooses actions. It can be deterministic. Always choose the same action for the same observation. Or it can be stochastic. Choose actions with probabilities. Stochastic policies are common in RL because they help exploration. If the policy always does the same thing, it may never discover better strategies. So you might hear something like, the policy outputs a distribution over actions. That just means it assigns probabilities like 60% go left, 30% go right, 10% jump. In modern RL, the policy is typically a neural network. You give it the observation, it outputs action probabilities or continuous control values. Finally, the agent needs a goal in mathematical form. That's the objective. In reinforcement learning, the objective is usually maximize expected return. Expected is there because environments can be random and policies can be random. So we're maximizing the average long-term reward the agent gets when it runs. So the policy is what we change during training. The return is what we want more of. The objective is the sentence that connects them. Find a policy that gets high return. This is the foundation of basically everything. Value-based methods, policy gradient methods, actor-critic methods. They're all ways of improving a policy to maximize expected return. So now you've got the RL vocabulary. An agent interacts with an environment, sees state or observations, takes actions, receives rewards. Over episodes, it produces trajectories, and we care about return, which often uses the discount factor gamma. The policy is the agent's strategy, and the objective is to maximize expected return. In Part 3, we'll step back and look at the formal framework behind most reinforcement learning problems. Markov Decision Processes, MDPs. We'll break down what an MDP is and the key assumptions it makes, then unpack how transition dynamics and reward functions define the behavior of an environment. Finally, we'll cover what changes when the agent can't see the full state, introducing partially observable settings, POMDPS, and why they matter in real-world RL. If you want, drop a comment with the domain you care about most: games, robotics, recommendations, or LLMs, and I'll tailor examples in the next videos. And if this helped, subscribe so you don't miss Part 3.